All right, let's go. Number 10. Roman surgical steel, the blades that match modern medical grade. Roman surgical instruments have been recovered from sites across the empire, with one of the most significant collections from the House of the Surgeon in Pompeii, sealed by Vesuvius in 79 CE. The collection includes scalpels, forceps, and specula, whose basic design is functionally indistinguishable from modern equivalents. In 2007, metallurgical analysis of Roman surgical blades using modern spectroscopic techniques found something more specific than design similarity. The carbon content and crystalline structure of the steel was consistent with the requirements for modern surgical-grade steel, material capable of holding a fine edge while resisting corrosion and brittleness. Producing steel with this carbon content requires controlling furnace temperature within a narrow range. Too little carbon and the blade cannot hold an edge. Too much and it becomes brittle, prone to fracture exactly where you do not want a surgical blade to fail. But here is where the achievement becomes more than a metallurgical footnote. Roman blacksmiths achieved this control without thermometers, without theoretical understanding of carbon's role in steel's molecular structure. They achieved it through generations of empirical practice, watching the color of heated metal, controlling quench timing, repeating what worked. The result was steel performing at a level Western medicine would not systematically reproduce for over 1,500 years. The scalpels are in the Naples National Archaeological Museum. Their edges, after 2 millennia, retain a microstructure analyzed by instruments their makers could not have imagined. Number 9. The Festos disc, printing technology, 3,600 years before Gutenberg. In 1908, archaeologist Luigi Pernier excavated the Minoan palace of Festos on Crete and recovered a fired clay disc, approximately 16 centimeters in diameter, covered on both faces with 241 symbols arranged in a spiral. The disc dates to approximately 1700 BCE. What makes the disc extraordinary is not the symbols, it is how they were made. Close examination reveals the symbols were not incised by hand, the way every other piece of Bronze Age writing was produced. They were stamped, each symbol impressed into wet clay using an individual carved seal, pressed and removed, leaving a sharp, repeatable impression. This is the fundamental principle of movable type, individual character stamps that can be combined and recombined to produce any text sequence, rather than carving each instance from scratch. But here is where the timeline becomes almost impossible to process calmly. Gutenberg's printing press, using movable metal type, is dated to approximately 1440 CE. The Festos disc, if the stamping interpretation is correct, demonstrates the same fundamental principle approximately 3,600 years earlier. The technology did not propagate. No other Bronze Age stamped texts using this method have been confirmed. The disc is in the Heraklion Archaeological Museum. The 45 distinct symbols remain undeciphered. We know, with reasonable confidence, how it was made. The method was, in principle, the printing press, sitting unused for 3.5 millennia. Number 8. Ancient Egyptian glass, temperature-controlled color production. In 1500 BC, glass production in ancient Egypt reached industrial-scale sophistication by approximately 1500 BC, with major centers at Amarna and Malkata. Egyptian glassmakers were producing a controlled range of colors, deep blues, reds, yellows, using metallic oxide additives whose color output depends critically on the precise temperature and chemical atmosphere of the furnace. Red glass production is particularly demanding. It requires a reducing, oxygen-poor furnace atmosphere maintained at a precise temperature, because copper oxide under oxidizing conditions produces an entirely different and undesired color. Egyptian glassmakers achieved consistent red glass production at industrial scale, requiring control not just over temperature, but over the ratio of oxygen to fuel in combustion. But here is where modern materials scientists find the achievement genuinely difficult to explain. Replicating ancient Egyptian red glass in modern laboratory conditions, even with full knowledge of the chemistry, has proven difficult. The consistency Egyptian glassmakers achieved across large production runs suggests a level of repeatable, teachable process control, implying empirical understanding of furnace chemistry that was never written down in any surviving text. Egyptian glass objects are in museum collections worldwide, their colors as vivid today as 3,500 years ago. The furnaces are gone. The knowledge was documented in glass, not words. We are still working out exactly how they did it. Number 7. Incan suspension bridges. Engineering the West didn't match for 400 years. The Inca road network, the Capacñan, stretched over 30,000 kilometers across the Andes, crossing river gorges that could not be bridged with available timber or stone construction. The Inca solution was the fiber suspension bridge, woven from ichu grass into massive braided cables, spanning gorges up to 45 meters wide, capable of bearing loaded llama trains continuously. The cables were engineered structures, woven in a multi-strand braiding pattern distributing load across the fiber bundle, requiring periodic systematic maintenance. Entire communities were assigned, as a state labor obligation called mita, to rebuild specific bridges on a regular cycle. But here is where the comparison to Western engineering becomes uncomfortable. The fundamental principle, load-bearing cables suspended between anchor points, with the roadway hung from the cables, is identical to the modern suspension bridge, from the Brooklyn Bridge to the Golden Gate. The first major Western suspension bridges at comparable scale were not built until the 19th century. 300 to 400 years after the Inca were operating a continent-spanning network of working fiber suspension bridges as standard infrastructure. The Quechua Bridge over the Apurimac River is still rebuilt annually by Quechua communities using the same methods and the same communal labor structure documented since before the Spanish conquest. The only suspension bridge of its kind, still functioning exactly as Inca engineers designed it. Number 6. The Banu Musa Programmable Flute, the first machine that could be told what to do. In 9th century Baghdad, during the Islamic Golden Age, 3 brothers known as the Banu Musa worked at the House of Wisdom. Around 850 CE, they completed a treatise documenting approximately 100 mechanical devices of their own invention. Among these was an automatic flute player, a mechanical instrument using a programmable cylinder studded with pins in specific positions, controlling which holes on a flute mechanism opened and closed, with a water-driven air supply producing the tones. Changing the arrangement of pins changed the melody. This is, in the strict technical sense, a programmable machine. The cylinder is the program. The pins encode instructions. Change the program and the machine's behavior changes, with no modification to the underlying mechanism required. But here is where the achievement's full weight becomes apparent. This is the same fundamental principle underlying the player piano, the music box, and the punched card systems used in early computing. Historians of computing widely recognize the Banu Musa device as the first documented programmable machine in human history. The next significant advance, Jacquard's punch card-controlled loom, which directly inspired Charles Babbage's conception of the programmable computer, was not developed until 1804, over 950 years later. The conceptual leap, separating instructions for behavior from the physical mechanism, encoding them in a removable format, is the foundational insight of all modern computing. It sat documented in a manuscript for nearly a millennium before anyone built on it. Number 5. Zhongheng's seismograph, the device that detected an earthquake 400 miles away. In 132 CE, Chinese polymath Zhongheng, chief astronomer to the Han Dynasty court, presented a bronze vessel approximately 2 meters in diameter, surrounded by 8 dragon heads each holding a bronze ball, with 8 bronze toads positioned beneath them with open mouths. The device detected earthquakes. When a tremor occurred, a ball would drop from a dragon's mouth into the toad beneath it, indicating the direction of the seismic event, even when no tremor was felt at the device's location. In 138 CE, according to the book of the later Han, the device dropped a ball indicating an event to the northwest, despite no felt tremor in the capital. Days later, messengers reported an earthquake in Longji province, approximately 400 miles away. But here is where modern engineering analysis turns historical anecdote into confirmed mechanism. Zhongheng's original device did not survive. Only the textual description remains. In 2005, Chinese seismologists, led by Feng Rui, constructed a working replica based on the historical description, using a pendulum-based mechanism responding to specific frequencies of ground motion. The replica functioned, successfully detecting simulated seismic events and indicating direction of origin. Zhongheng had built a functional seismograph 1,700 years before the first Western seismograph, developed by Luigi Palmieri in 1855.
Number 4. The Greek odometer, automated distance measurement for Roman roads. The Roman architect Vitruvius, writing in De Architectura around 25 BCE, described a mechanical device for automatically measuring distance traveled by a cart. The device used gears connected to the cart's wheel, calibrated so a specific number of rotations, corresponding to a known distance, would release a pebble into a collection box. At journey's end, the number of pebbles multiplied by known distance per rotation gave the total distance traveled, requiring precision gear cutting and an understanding of translating continuous rotational motion into discrete, countable events. But here is where the broader implication becomes significant. The Roman road network, the cursus publicus, required accurate distance measurement to place milestones at consistent intervals across thousands of kilometers, supporting military logistics and administrative communication. The odometer made this systematic and independent of human pacing error. The same gear-based principle, converting rotational motion into a countable mechanical record of distance, is the direct conceptual ancestor of every mechanical odometer used in vehicles through the late 20th century. The Romans were running mechanical trip computers on their carts over 2,000 years before a 1990s automobile dashboard performed the same calculation electronically. Number 3. The Nimrud lens, ground optical glass that predates spectacles by 2,000 years. In 1850, British archaeologist Austin Henry Layard, excavating the Assyrian city of Nimrud in northern Iraq, recovered a small piece of rock crystal, approximately 4 centimeters in diameter, plano-convex in shape. The object dates to approximately 750 to 710 BCE, during the Neo-Assyrian Empire. Examination shows it was ground and polished deliberately, producing a curvature that functions as a simple magnifying lens with a focal length of approximately 11 centimeters. The Assyrians possessed a ground optical lens, manufactured through a process requiring precise control over curvature and surface polish, approximately 2,700 years ago. The conventional history places the first documented corrective or magnifying lenses, as eyeglasses, in 13th century Italy, over 2,000 years later. But here is where the lens's actual function becomes the genuinely unresolved part of the story. Some researchers, including Italian scientist Giovanni Pettinato, have proposed Assyrian astronomers use the lens with other instruments to observe celestial objects, citing detailed astronomical records describing observations difficult to explain without optical assistance. Others maintain it was a decorative object or engraving tool with incidental optical properties. The lens is in the British Museum. Its optical properties are measurable and confirmed regardless of original purpose. Whether the Assyrians deliberately exploited those properties has not been resolved. Number 2. The Roman hypocaust. Central heating not matched until the 20th century. The Roman hypocaust system, in widespread use by the 1st century BCE, was central heating that warmed entire buildings, public baths, villas, residential complexes, from a single, centrally managed heat source. The floor was raised on short brick pillars, creating a hollow space beneath. A furnace generated heat channeled into this space, warming the floor through direct contact with heated air. Hollow ceramic tubes embedded in walls carried hot air and smoke further upward, heating the walls before venting outside. The result? A building heated evenly through floor and wall radiant heat, from a single fuel source, without smoke or open flame in occupied space. But here is where the comparison to subsequent European technology becomes disturbing. Following Rome's fall, hypocaust technology fell out of widespread use across most of Europe. For approximately 1,000 years, medieval European buildings were heated primarily by open hearths, radically less efficient, exposing occupants to significant smoke, incapable of evenly heating large structures. Systematic central heating, applying the same principle of distributing heat through radiant floor and wall surfaces, was not widely reintroduced until modern radiant floor heating in the 20th century. For roughly a millennium, Europeans were colder, in smokier rooms, than the Romans who had lived in the same territories centuries earlier. The hypocaust ruins at Bath in England and Pompeii in Italy still stand, Hollow brick pillars in rows beneath floors that have not held heat in over 1,500 years.
Number 1. Hero of Alexandria's steam engine, the Industrial Revolution that never happened. In approximately 50 CE, the mathematician Hero of Alexandria documented a device in his treatise Pneumatica that functioned as a working steam engine. The aeola pile, a sealed sphere mounted on an axis, connected to a water-filled boiler by 2 hollow tubes. When heated, steam traveled into the sphere and escaped through bent nozzles on opposite sides, causing the sphere to spin rapidly through reaction thrust. This is a functioning steam turbine, converting thermal energy into mechanical rotational motion using the same physical principle that powers every steam turbine ever built, including those generating a substantial portion of global electricity throughout the 20th century. Hero's device worked. It has been reconstructed multiple times and functions exactly as described. But here is where the most consequential question in the history of technology arrives, with no satisfying answer.
The Industrial Revolution, beginning in Britain in the second half of the 18th century, was driven by practical steam engines. Thomas Newcomen's atmospheric engine in 1712, then James Watt's improved design in 1776, performing useful mechanical work at scale. Hero's aeola pile demonstrated the core physics underlying steam power approximately 1,700 years before Newcomen's engine. Rome possessed sophisticated metalworking, extensive engineering knowledge, and a labor-intensive economy built on mining and manufacturing that could have benefited directly from mechanized power. It was treated as a toy. Hero's surviving writings describe it primarily alongside temple doors that appeared to open through hidden mechanisms and coin-operated dispensers, demonstrations, and curiosities. There is no surviving evidence anyone attempted to scale the aeola pile principle into a device performing useful work. The leading explanation involves the abundance of slave labor in the Roman economy, reducing the incentive to mechanize physical work, combined with the absence of institutional frameworks, capital investment, a manufacturing economy oriented toward productivity, that made steam engines economically valuable enough to refine in 18th century Britain. The physics was available in 50 CE. The metallurgy was available. What was missing was everything else. Hero's device is reconstructed and displayed in science museums worldwide, spinning exactly as it did in Alexandria nearly 2,000 years ago. For 1,700 years, it spun, and nothing happened. 10 technologies. 10 moments when ancient engineers, working with bronze, clay, glass, and stone, achieved results we did not systematically match again for centuries. In the most extreme case, for nearly 2 millennia. Surgical steel, matching modern medical-grade specifications, achieved through empirical metallurgy with no theoretical understanding of carbon chemistry. A printing technology sitting unused for 3,600 years before Gutenberg. Temperature-controlled glass color chemistry that modern laboratories still struggle to fully replicate. Suspension bridge engineering that outperformed Western technology for 400 years and is still functioning, rebuilt by hand every year in the Andes. The first programmable machine built in 9th century Baghdad with no successor for nearly a millennium. A seismograph that detected an earthquake 400 miles away in the 2nd century CE, 1,700 years before the West built an equivalent.
A mechanical odometer running on Roman carts 2 millennia before your car's dashboard performed the same calculation. A ground optical lens manufactured 2,700 years ago, sitting in a museum case with its functions still debated. A central heating system that warmed Roman buildings more effectively than European buildings would be heated for the following 1,000 years. And a working steam engine that demonstrated the core physics of the Industrial Revolution 17 centuries before anyone put it to work. What connects all 10 is not that ancient people were, in some general sense, technologically advanced. In each case, the foundational physical principle, the engineering insight, the technical capability existed, working, demonstrated, sometimes deployed at scale. And in each case, something other than technical capability determined whether that knowledge propagated and transformed the world, or sat documented and unused until rediscovered centuries or millennia later.
The limiting factor was never physics. It was never engineering skill. It was economics, institutions, the specific and fragile set of social conditions that determine whether a working idea becomes a civilization-altering technology or a curiosity that sits unread until someone happens to translate it again. Hero of Alexandria held the Industrial Revolution in his hands in the year 50 CE, set it spinning on a tripod, and used it to entertain visitors to his workshop. The steel was right. The mechanism was right. The physics was right. The world it could have built waited 17 centuries for someone else to build it instead. If you want to see more videos like this, click the video on screen now, and make sure to subscribe.